All right, so the title of this module is Linear Algebra, Matrix Operations, and Solving Systems of Linear Algebraic Equations. So let me put up this title so that you know what I'm talking about. Linear Algebra, Matrix Operations, and Solving Systems of Linear Algebraic Equations. All right, so let me start with a brief background so that you are a bit prepared. All right, so what is a matrix? The matrix is a collection of numbers. Matrices can have not necessarily equal number of rows and columns. So for example, this matrix has n rows and m columns. I'm going to say, the way to say it mathematically is this. So A belongs to the class of matrices that are n by m, n rows and m columns. So for simplicity, I'm going to use this notation so that to save myself the words instead of saying matrix A has n columns and n rows and m columns. I'll just say this. Okay. And I will specify what that means. So A has n rows and m columns. Okay. You can transpose the matrix. I'm sure you've seen that symbol before, A transposed. That means that whatever used to be row becomes a column, and respectively whatever used to be a column becomes a row. So this will look like this. You just flip those. And this this matrix becomes m by n. This is transpose matrix. It has m rows and n columns. Okay. If A and B matrices are of the same dimensions, in other words, they're n by m, you can add them or subtract them, multiply them by the numbers, and add them up again. So if A is n by m and B is n by m, then you can define something like A plus B or A minus B, or take a scalar alpha multiplied by A, take scalar B multiplied by B, and add them up. So all of those things exist. You can also multiply matrices one by another, but in order for the matrices to be multiplied, they have to be of compatible dimensions. In other words, if A and B, for A to be able to, for us to be able to multiply A with B, A has to have the same number of columns as the number of rows in B. So if, in other words, if A is n by m and B is m by k, then the product of two matrices, please review how two matrices get multiplied. So A times B is not the product of the corresponding elements. It's the ijth element of A times B is formed by multiplying the ith column of A with the jth column of B. Hopefully you remember that. If not, please review that. So in this case, A times B will be an n by k matrix, and it exists. You can obtain that. And let me show you how to do this manipulation. So let me open up the first file. Okay. So let's say I'm defining a non-square matrix A. You can take the transpose of this matrix. Let me comment everything out so that you're not confused. You can take the transpose. So you can see here that one is a matrix and the other one is a transpose of that matrix. So the columns become rows, 2, 3, minus 5, 11, and so on. So this, the command for taking the transpose is apostrophe. You can add two matrices if they are of the same dimensions, as I mentioned to you. So you define the matrix B, which is also, in this case, 3 by 4. And you can add them up or subtract them or do whatever you want. So this is going to be the result. Multiplication, if two matrices are of compatible dimensions, and by compatible dimensions, as I said, that means that A has the same number of columns as the number of rows in B. In that case, you can do A times B. Well, in this case, since I already used up the symbol for B, I'm using the C. So C would have to be have 3 rows and whatever number of columns. I'm choosing that to be 3 as well. 4 columns. 4 rows for C, because the number of columns for A is 4. In that case, you can do the multiplication of both matrices. So A times C is going to produce this matrix. Okay, now let me switch back and talk about the rank. The rank of a matrix is a concept that is defined for any matrix, not necessarily a square matrix, any matrix n by m. And I'll tell you in a second what that means. So if A is a n by m matrix, then the rank of a matrix is the maximum number of linearly independent rows or columns of this matrix. If you need to refresh your memory on what is the linear independence of vectors, please refresh it. But MATLAB basically uses the definition of linear independence in order to compute the rank of a matrix. It's done through a very simple command called rank. So we're switching back to that code. So MATLAB is going to compute the maximum number of linearly independent rows or columns. It's the same thing through the command called rank. So remember, my matrix A was 3 by 4. So the maximum number of linearly independent columns or rows has to be 3. So it has to be minimum number between columns and rows, because the number of linearly independent ones is the same, has to be the same. So let's see what it is. So all rows of matrix A are linearly independent. That means that the rank of A is equal to 3. So this is how you compute the rank of a matrix. Let me switch back to the sort of a lecture part of it. There are certain things that pertain to a square matrix. So if the number of rows is the same as the number of columns, then A is n by m is considered a square matrix. For a square matrix, we can define the so-called inverse. So A inverse, if it exists, it may not exist, but if it exists, is another n by n matrix such that its product with A gives you the identity matrix. Identity matrix is a diagonal matrix with ones on the diagonal and zeros everywhere else. The property of the identity matrix is such that if any square matrix is multiplied by an identity matrix, the result is the same square matrix that was initially multiplied by the identity matrix. Very much like 1 in the world of scalars. Okay, this is that, and another thing that pertains to the square matrices is the determinant. Of a square matrix. Okay. Let me not remind you what the determinant of a n by n matrix is. It has something to do with the so-called minors. MATLAB will calculate the determinant for you. Let me just maybe remind you that the determinant of a 2 by 2 matrix is given by the product of diagonal elements minus the product of the off-diagonal elements. Just remember that. But the definition of the determinant of an n by n matrix involves something like this. So determinant of A, if it's an n by n matrix, is going to be A11 times minor 1, 1 minus A12 times minor 1, 2 plus A13 times minor 1, 3 and so on, minus 1 to the power of n plus 1 times minor m1n, where the m1n is a minor which is obtained by eliminating the first row and ith column of the matrix A. Now, again, this is a formality. It's not the subject of this module to discuss extensively what the determinant is. Our objective is to be able to obtain the determinant via the MATLAB. And it's done through a very simple command called det, determinant. So let's switch back to the MATLAB, and I walk you through how to obtain the determinant of a square matrix. So let's talk about square matrix. And for square matrix, we can define an inverse if it exists. If the inverse doesn't exist, in other words, if the determinant of a matrix is equal to 0, the MATLAB will tell you. But in this case, so I'm defining the square matrix 4 by 4. And the inverse is done through the inv command. So if you run this, then you're going to get the inverse of a matrix. And then you might as well verify that you indeed obtained the inverse. And you do so by checking whether A times A inverse indeed gives you the identity matrix. You can do that, and you can see that it is indeed an identity matrix. You can obtain the determinant of a matrix, of a square matrix, through the command det. That's what it is. The rank of the matrix of a square matrix, well, if the determinant of a square matrix is not equal to 0, that means that all columns are linearly independent, which means that the rank is going to be equal to the size of the matrix. So it's natural to expect that rank to be equal to 4, and it is indeed. If the determinant of a square matrix is equal to 0, then the rank of that matrix will be anywhere between 1 and n minus 1. All right, another important concept called eigenvalues and eigenvectors. Let me again go back to my write-up and give you some brief introduction to what the eigenvalue and eigenvector problem is, and then we'll see how to handle this in MATLAB. So eigenvalues and eigenvectors of the matrix A only for the square matrix who can define eigenvalues and eigenvectors are respectively a scalar lambda. In general, it's a complex number. This is how I define complex numbers. And the vector, also complex in general. Let's call this eta. It's an n-dimensional vector such that they satisfy this equation. A times eta is equal to the eigenvalue times eta. Okay. So in MATLAB, there is a command called EIG that handles the calculation of the eigenvalues and eigenvectors. Okay, so you define the matrix A1, which I did earlier, right here. You type up EIG, and if you just type EIG and hit enter, MATLAB will give you the eigenvalues. If you type up something like this, then MATLAB will give you, so I write here, a matrix V, which is the matrix whose columns are eigenvectors of the matrix A, and the matrix D, which is a diagonal matrix that has eigenvalues of A on the diagonal. So you get the complete picture of what the eigenvalues are and what the eigenvectors are. So if you hit that, you're going to get this. So V is a matrix whose columns, so this first column, second column, third column, and fourth column, are eigenvectors of the matrix A, which are complex in general. And D is a diagonal matrix. You can see that this is indeed a diagonal matrix with the eigenvalues of the matrix A on the diagonal. So this is how you can extract those eigenvalues and eigenvectors. You can verify that you indeed got what you were looking for by setting up that equation that I showed you earlier, this one, A times eta times is equal to lambda times eta. So you're basically setting up A times eta minus lambda times eta, and that better be equal to 0. So this is how you do this in MATLAB. A times V minus V times D should give you a 0 matrix. And you can see in the MATLAB language, it is indeed 0. So anything that is 10 to the power of minus 13 is viewed to be 0. So you got this right then, that means. You can find it an alternative way of verifying by checking this for individual eigenvalue and eigenvector. So you're taking the first eigenvalue multiplied by the first eigenvector, and putting it into the context of A times the eigenvector minus eigenvalue times the eigenvector should be 0. So if you run this for each eigenvalue and eigenvector, you're going to get 0 as well. So you get a bunch of zeros. Again, in the MATLAB language, e to the 10 to the power of minus 14 is viewed to be 0. I want to show you a little bit of remind you maybe perhaps a property, let me go back to my notes, that suggests that the trace of a matrix, which is the summation of the diagonal elements, is actually the summation equal to the summation of the eigenvalues of the matrix. So if you compute eigenvalues and sum them up, that should be equal to the summation of the diagonal elements of the matrix A. That's one property of the eigenvalues. Another property of the eigenvalues is that the product of all eigenvalues is equal to the determinant of a matrix. And since we have everything set up, might as well check if this is true. So the product of the eigenvalues, the product of the eigenvalues is equal to the determinant of a matrix. So I'm just taking the diagonal elements of the matrix D and multiply them all together and compare it with the determinant. The difference should be equal to 0. Indeed, it is equal to 0. Something 10 to the power of minus 12 is considered to be 0. And you can do the same thing with respect to the trace here. So you can check the trace as well. So the trace of the matrix is equal to the sum of the eigenvalues, and you can verify that the difference between the trace and the sum of the eigenvalues is indeed equal to 0. There are some special matrices that you might have to deal with in your courses. So like identity matrix. Identity matrix is defined through the command called EYE, and in the brackets you specify the size of the identity matrix. It has to be a square matrix, n by n, so you specify only one number. The matrix that consists of zeros, sometimes you might have to use that as well. This is done through the command zeros, and you specify the size of that matrix. 3 by 2, matrix of zeros with the size of 3 by 2. Matrix of ones, matrix whose entries are equal to 1. It's done through the command ones. For example, here I'm saying 5 by 8 matrix of ones. And then there is a command called rand, which generates the random numbers, and you can generate a matrix whose entries are randomly generated numbers. Though those numbers will be between 0 and 1. So the value of those numbers will be between 0 and 1. So I'm generating here the matrix 2 by 3, each entry of which is a random number. So you can see all of that. So this is the randomly generated matrix. This is the matrix of ones, and this is the matrix of zeros. Okay. In some assignments, you might have to build a matrix using this structure, such as matrix of ones, zeros, and so on. You can do this in MATLAB. So for example, you have an 8 by 8 matrix whose first block is the identity matrix 4 by 4. The second block is the matrix of ones. The block underneath is some matrix A1, and the block right next to it is the inverse of A1. You can do that, and you can compute the eigenvalues of that combined matrix. So it's going to be 8 by 8 matrix. So this is going to be my matrix G, which is going to be 8 by 8, and then I compute its eigenvectors and the eigenvalues. Those are going to be down through the given through the matrices 8 by 8. One of them is diagonal, and another one is the matrix whose columns are going to be the eigenvalues of the matrix G. In some courses, you might have to deal with symbolic matrices. Let's see how we handle this. You define symbolic variables. In this case, let's say it's going to be the symbolic variable is going to be theta. In general, symbolic variables are viewed as complex variables, but if you want to specify that your theta is indeed a real variable, you just add real here. Let's say you define this in mechanics. That's called that's one of the transformation matrices using Euler angles. So the matrix of cosine theta, sine theta, minus sine theta, and cosine theta. So this is how you formally define a symbolic define matrix symbolically. MATLAB can symbolically compute the determinant of this matrix. So let's see how that is handled. So let's excuse MATLAB for not knowing all the trigonometric identities, but it gives its best shot. It's cosine squared plus sine squared. We know it's equal to 1. MATLAB doesn't know this, but that's okay for our purposes. You can you can calculate the eigenvalues, again symbolically. You can do the transposition, obtain the transpose. So these are the eigenvalues of the symbolically defined matrix. So it's again given in terms of cosine, in terms of theta. Transposed matrix, MATLAB can do the transposition. You can also evaluate the matrix at some values of theta. So evaluating T eigenvalues of the matrix T, determinant of T, at a specific value of theta. We've done that before. This is done through the subs command. So I'm implementing subs command. In the expression for T, I'm going to replace theta with some value of my choice. Let it be pi. Same thing in the eigenvalues and same thing with the determinant. So you get this. So see, MATLAB does compute that determinant to be equal to 1 for a specific value of theta, but again, in a symbolic structure, it doesn't know that sine squared plus cosine squared is equal to 1. Okay.